Hey, welcome back. Today we're going to continue talking about applications of positive semi-definite matrices by talking about spectral clustering. Okay, and this lecture piggybacks on the lecture from last time. So let me just recall some important details from last time. Okay, so G is going to be a graph, right? In general, we'll write G, V, E, where V is the vertex set, E is the edge set, and V for us will always just be, we'll label them with the natural numbers from 1 through n. Then we defined the Laplacian matrix of G was defined to be LG, which was DG minus AG. Here, DG was the diagonal matrix of the degrees of each vertex. And AG was the adjacency matrix. And last time what we saw is that this Laplacian is always a positive semi-definite matrix. A positive semi-definite matrix. And so since it's positive semi-definite, it means that all of its eigenvalues are non-negative. And we saw that 0 is always an eigenvalue. And so we can list the eigenvalues of LG. By convention, we list them from smallest to largest. 0 is always an eigenvalue. And then since all the eigenvalues are non-negative, we can list them from smallest to largest like this. Because it's a real symmetric matrix, it has n real eigenvalues, counting multiplicity. And we said that one use of this is that this second eigenvalue, which we said you could also call the Feedler value, can detect whether or not your matrix is connected. Your matrix is connected if and only if the Feedler value, the second smallest eigenvalue, is positive. And in fact, the number of times that 0 is an eigenvalue tells you exactly the number of connected components of your graph. Okay, today we're going to look at the Feedler vector, which is the eigenvector associated to the second smallest eigenvalue, right? So an eigenvector for lambda 2 with eigenvalue lambda 2 is called the Feedler vector. Okay, and we're going to use those things today to study spectral clustering. Okay, so first, a couple of notes. The first note is you should consider part of taking part in this lecture to be to actually implement in code the example that's not done for you in the notes. Okay, so together, so I'll switch to Julia later on. I'll go through a little bit of one example about how to do this thing, to use spectral clustering to use the graph Laplacian and try to understand something about clustering in your graph. But watching me do it is not really going to teach you anything. So you really need to go into Julia or your preferred software and do it yourself. Okay? This lecture is really based on what used to be a starred homework problem. So you should spend some amount of time. I mean, starred homework problems take a long time. I'll sort of walk through the process, which should make it faster, but you still want to, I still think that you want to learn this process, and so you should actually implement in code. Okay, so what is spectral clustering? It's a way to try to understand the clusters in a graph. Okay, so what is a cluster? So we will use really the Feedler vector and the graph Laplacian to understand clusters in a graph. Okay, so what is a cluster in a graph? So let me speak from an intuitive perspective. A cluster is some subset of nodes, some subset of vertices in your graph, where there's a lot of connections between those nodes and relatively less connections to the rest of the graph. Okay, so you have some huge graph, and generally, one thing that you might be interested in is what are the clusters in my graph? Right, so for example, maybe if I took the the graph of all of the college students in Washington, right? Or maybe even Seattle, whatever, right? And I looked at who they're friends with on Facebook. So actually, I don't know if kids your age are really all into Facebook. I assume you all probably have Facebooks. It was bigger back when I was in college. But we could look at just the Facebook accounts of all the people who are college students in the state of Washington, and you can look at all the friendships among them, right? And what you would expect to see from an intuitive standpoint is sort of all the students who are at UW Seattle. There's going to be a lot of connections between them, right? Of course, not very many people are connected to like everybody that goes to UW, but there should be relatively a lot of connections within this UW Seattle group. Then maybe you should see a lot of connections within like the UW Buffalo group and relatively few connections between compared to the number of connections that you have within this cluster. And like maybe Seattle U. So you should be able to find some groups of vertices that are more connected to one another than they are to the rest of the vertices in the graph. And there's of course lots of applications for why you might want to understand the clusters in a graph. So for example, let's say you wanted to advertise to certain Facebook users, right? Then understanding the clusters in your graph might tell you something about the groups of people, how they're grouping off, and maybe that is indicative of something of their interests, right? So if you had I don't know, right? If you're going to advertise Seattle U gear versus UW gear, then it might be nice to know where the clusters are in this graph, and then you can target your advertising to the correct group, right? Or if you want us to study, say, the spread of some disease, right? Then knowing the clusters in your graph sort of tells you where you would expect the disease to spread around, like which people are sort of more susceptible to get the disease based on where you found the disease. So understanding the clusters in a graph is a very useful, important thing. Okay, and it's still an active area of research, how to understand clusters in a graph quickly. So today we're going to try to understand a little bit about finding clusters in a graph. Today we're going to explore an algorithm that will output an approximation of the two clusters in a graph. In other words, it'll try to cut your graph in half or into two sets of vertices where the two sets are sort of more connected within each other than they are between the two parts. Okay, so for our running example, we will use the following graph that's written in the notes, but this is not the one that you should do the problem on. This will be the one that I'll work with. Okay, so I'll label its nodes like this, counterclockwise. And okay, so in the notes, this 10 and 9 are switched, but it doesn't actually change the graph. So I think it's more pleasing to draw it this way, so I'll draw it this way. Okay, so this will be our running example. And if you were to look at this graph and you were to say, okay, well, are there any natural clusters in this graph? Or more specifically, is there a natural way to divide this to two clusters? Then from looking at it, it's kind of clear that this group of 5 vertices sort of forms one cluster, and this group of 5 vertices sort of forms the other cluster, right? That's because within this red group of vertices, there's sort of a relatively large number of edges. Within the green cluster, there's sort of a relatively large number of edges, but there's not very many edges going between the red and the green clusters. Okay. But you can't find clusters just by looking, right? In particular, if you are Facebook and you have 100 million users, you can't just look at that with like a lot of friendships in between them, right? You can't just look at that and say, oh, here's a cluster, right? You can't even visualize 100 million points at once, right? So we want to have some quantitative way, some quantitative measure that should give us some idea of the clusters in a graph. Okay, so what we're going to talk about is we're going to talk about cuts in graphs, and we're going to study an algorithm that will give us one cut, which will cut the graph into two pieces that are approximations of the two clusters in the graph. Okay, so let me just set up some notation, first of all. Okay, so if you have two sets x and y, x and y are sets, then this notation, x minus y, is the set of all elements that are in x, but they're not in y. Okay, so that's what you call the set theoretic difference. You're just taking all the stuff in, you're taking x and you're just removing all the stuff that happens to be in y. Okay, we use this absolute value notation. This is for the size of x, or the cardinality of x. So, for example, if I call this set A, it's 4, 5, 6, 7, 8, then remember this graph, just remember that has vertex set V and edge set E. So the vertex set here is 1 through 10. So if I take V minus A, what I mean is the vertices 1, 2, 3, 9, 10. Because all I'm doing is I'm just taking the set of vertices and I'm removing all the vertices that are in A. Right, and of course, the size of A here is 5, or the cardinality of A is 5. Sorry. A equals 5. Okay. So that's just some standard terminology. Let me now define what a cut is. So a cut in a graph G is a partition of V into two sets, A and V minus A, so where A is a subset of V. And this is sometimes called the cut induced by A. Okay, so a cut is really just you take some vertices and then you take all of the rest. You take the vertices in A, and then you consider all the rest of the vertices. And you can picture it as literally, like, you can either picture it as taking this set of vertices, if this is a set of vertices that will be my cut, or you can think of it as, oh, I'm going to draw a line between one set of vertices and all the rest of the vertices in the graph. That's why you might think of it as a cut. Okay, now, what quantitative measure do we have to get at whether the cut, whether any particular cut is really dividing us into nice clusters, two nice clusters? Okay, and the thing to notice here is, if I look at this cut, there's only one edge between the vertices in A and the rest of the graph. And there are many, many, many possible edges between the vertices in A and the rest of the graph, but only one of them is actually in our graph, right? So if I were to draw all the possible edges, right, there's like this one, 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 this, right? There's tons and tons and tons and tons of possible edges. But if I've chosen this set A, of all the possible edges, there's only actually one edge in the graph. It's the one that goes between 1 and 6. And so the fact that there's very few edges, way less than are possible, suggests that this group of vertices in A is not very connected to the rest of the graph. And so that's a metric that we can actually use. So here's some notation. If x and y are sets of vertices, we'll let E sub xy denote all edges with one vertex in x and one vertex in y. Okay, so, I mean, this notation is suggestive. It's saying the edges from x to y. It's all the edges that go from x to y, or from y to x, right? It's symmetric in edges. Okay, so in our example, if I look at E of A comma B minus A, what this is this the set of edges where one of the vertices is in A and the other vertex is not in A. So for this specific A, this edges between A and V sub A and V minus A is just the single edge 1, 6. There's only one edge in that set. Okay. Now, the density of the cut induced by A is given the following notation. So it's phi of A comma V minus A. So we're going to use the Greek letter phi for density here. And it's going to be the size of this set, the number, in other words, the number of edges between A and V minus A, divided by the number of vertices in A times the number in vertices in V minus A. Okay, so what is this? This denominator counts all possible edges between V and A and the rest of the graph, right? For every vertex in A, you could have an edge to every vertex not in A, so you'll have exactly A times the size of A times the size of V minus A possible edges. And this counts the number of edges that are actually in your graph. So number of edges between A and the rest that are actually in your graph. And this is why it's called a density. It's called a density because it's how many edges there are compared to how many edges there could be. Okay, so for this example, there's 5 vertices on the left and there's 5 vertices on the right. So there are 25 possible edges between A and the rest of the graph, but there's only one edge that's actually in our graph. Right, so maybe I should have done all these examples in red, but let me just do that here. So for us in the example, this was 1 over 25. Right, meaning that, sorry. I forgot a very important factor, which you have to multiply by n. I guess it's not that important because you're always multiplying by the same number, but this is in the definition of density. So it's actually 10 over 25 because there's 10 vertices. Okay, so in order to try to find the best possible clusters, what we should be looking for is a cut where the density is very, very low. In other words, there's not very many edges. And if you can cut somewhere where there's very, very few edges, you're going to separate your graph into two pieces where they were sort of more connected to one another, within each group than they were between the groups. Okay, so we'll let phi sub g denote the smallest possible density of a cut in G. Okay, so if you look at all possible cuts, you look at all their densities, there are only finitely many cuts, and so there will be a smallest one. And so you call that smallest possible density phi sub g. That's a unique number. And any cut with density as small as possible is called a sparsest cut. Okay, and there could be more than one sparsest cut. Now, finding the sparsest cut in a graph is, I believe, an NP hard problem. And if you think about why, how many possible, if your graph has n vertices, how many possible cuts are there? It's just the number of subsets of the vertices, right? Every single subset of your vertex set is a possible cut, which means that there's roughly 2 to the n possible cuts. So if you have a humongous graph, 100 million vertices, there's 2 to the 100 million possible cuts. That's like way, 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 way more than the number of particles in the universe. So that gives you some idea of, as you have a large graph, it's going to be very hard to try every single possible cut, which is, at least from a naive standpoint, what it would take to find the sparsest cut. Okay, but it's an NP hard problem, or at least it's in NP to find the sparsest cut. And so finding approximations of sparsest cuts is what a lot of research is dedicated toward, right? If you can have a fast algorithm that will find you an approximate sparsest cut, then that's pretty good. And so today, using Julia, we will implement an algorithm that will give us a fairly sparse cut. Okay, so today we'll find an algorithm that gives a fairly sparse cut. Okay, and what do I mean by fairly sparse? Here's the theorem. So what is here's a theorem with two parts. Okay, so one is that phi sub g, this minimum possible cut density, is greater than or equal to lambda 2. So here again is an example where the eigenvalues, the spectrum of some matrix associated to a graph, the eigenvalues tell you some really deep information about the graph. I think this is pretty amazing, actually. The second smallest eigenvalue tells you how sparse a cut can possibly be. Right, by the way, if your graph is not connected, it's very easy to find a cut. You just cut between the disconnected components, and there's no edges there, so you get density 0. Right? So you would only really want to study this problem for a connected graph, but that's okay. If you have a disconnected graph, you just consider each connected component. Okay, so the sparsest density, the smallest possible density, is bigger than or equal to the Feedler value, and the algorithm that we'll implement, the algorithm finds a cut of density at most 4 times the square root of dg times lambda 2, where dg is the largest degree of a vertex in G. Okay, so this is a relatively sparse cut. It's not the best algorithm in the world, but it is one that we'll be able to understand the parts of. Okay, note that like dg is in general going to be much bigger than lambda 2. Right? dg could be like 10, right, if you have a very well connected vertex, where lambda 2 is probably going to be pretty small. We'll see that in some examples. So this quantity is probably going to be bigger than lambda 2. And so the algorithm that we're going to finds a cut that's at worst 4 times something that's probably bigger than lambda 2. But again, the benefit is that we can actually use some linear algebra that we know to find this relatively sparse cut. Okay, so I think now what I'll do is I'll switch to Julia, and so can show you sort of the implementation of this algorithm for this example. And then there's another graph that you can do on your own. Okay, so here I am now at a .jl file, which I'll be able to load into Julia. This way I don't have to type any matrices directly into Julia. If I make a mistake, I'll type them in my JL file and load them into Julia. Okay, so in this file, what I've done is I've typed out the adjacency matrix of the graph that's in the notes. Right, so if you look at that picture, which you can see, I don't have it on screen, but you can see it. The vertex 1 is connected to vertices 2, 3, 6, 9, and 10. So the first row of this adjacency matrix has a 1 in the 2, 3, 6, 9, and 10 positions, and also that's true in the first column. Okay, so this is the adjacency matrix of my graph. Then I set up the diagonal matrix, whose diagonal entries are the degrees. So in Julia, you can instantiate a diagonal matrix by capital diagonal and then giving it the set of entries in order. So I guess it's an array of entries. So vertex 1 has degree 5, vertex 6 has degree 5, and the rest of the vertices have degree 2. So this is the diagonal matrix consisting of degrees of the vertices. And my Laplacian is going to be dg minus ag. Okay, so what I can do is I can switch over to my command prompt, and I'm currently in the folder that has this Julia file. So let's run Julia. And what you can do is you can include the file that you want and hit enter. And okay, so it outputs something because I have something later on in the file. But let's just take a look. AG is supposed to be my adjacency matrix, which it is. You can check that for yourself. DG was my diagonal matrix. And so it's saying it doesn't know what these entries are, but it will treat them as 0. And then LG is my graph Laplacian, and it looks exactly the way a graph Laplacian should look. It has the degrees along the diagonal, and -1s representing the rest of the edges. Okay? Now, what do I need to understand? I need to understand the Feedler vector and the Feedler value of this Laplacian. What's the Feedler value? It's the second smallest eigenvalue. So let's take a look at the eigenvalues of my Laplacian. And you can see that they are all non-negative. This is 0, well, up to machine precision, I guess. This should be 0, so we know that this is 0. And the second smallest eigenvalue is 0.2984, etc. So my Feedler value is this 0.2984, etc., which means by the theorem, my sparsest cut will have density that's bigger than this, at least as big as this Feedler value. Okay, well, how do I find my Feedler vector? My Feedler vector will be the eigenvector corresponding to this second eigenvalue, so it should be this column of this matrix, right? So my Feedler vector should be this eigenvectors matrix, and I want to take the second column and all of the rows, and so my Feedler vector will be this thing. Okay, now what you need to do in the algorithm is you need to take this Feedler vector and you need to arrange the entries from largest to smallest. Sorry, from largest to smallest, right? So if you look at this list of entries, 0.23 is smaller than 0.3336, and there's several 0.336s. There's 4 of them, and that looks like the biggest one. Then the next biggest one looks like the 0.234. Then the next one is negative 0.234. The next one is negative 0.3362299, etc. And so I want to sort these, and I want to keep track of the order in which they're appearing. Okay, so I've done this also in this file. So here I've set up a matrix that's 10 rows and 2 columns. And the first column of this matrix is the Feedler vector, right? This is exactly the command I used to get the Feedler vector. And the second column of this matrix is the numbers 1 through 10. So just telling you which of the eigenvalues is associated with. And all I've done is I've just sorted this in order of the second column in reverse. So in order of the first column in reverse. So in other words, I've sorted it in order to list the entries in the Feedler vector from largest to smallest. That's all I've done here. Let me show you what I've done by going back to this command window and typing in FG. This is the non-sorted Feedler vector. And, right. This output of Julia at the very beginning, this one is the sorted Feedler vector. Okay, so what I've done is I've just written down a little brief snippet of Julia code to spit out the reordered Feedler vector. And as you can see, there's several 0.33s at the top, then there's a 0.23, a negative 0.23, and several negative 0.23s at the bottom. Okay, so what this says is this is the ordering of the eigenvalues or the eigenvalue labels going from the largest entry of the Feedler vector to the smallest. Okay, and it says in the notes that if you have a tie, you can break the die however you want. Okay, so I think in the notes, it's just broken as 2, 3, 9, 10. It's done in numerical order, but this is just what I'm getting out of Julia. So it doesn't matter how you do it. Okay, and now maybe I should switch back to the other view. Okay, so here I've just took a screenshot from the other view of the Feedler vector in order. Okay, so now what you do is you set up a bunch of possible sets. Okay, and the sets are set up sort of very simply. You start with the top of your list. I guess I could do this in brighter color. You can start at the top of your list, and then you just include one element at a time. Okay, so in your notes it's done a little bit differently, but I'll let A1 be the set just containing 9, A2 be the set just containing 9 and 3, A3 be the set just containing 9, 3, and 2, right? And I'll just keep on adding all the way down to A10, which will of course be all of the numbers, right? Okay, now what you do is you have these are 10 possible cuts, and you compute each of the cut densities. So compute the cut density phi of AK, comma, V minus AK. So let me do one example for you. Let's do the third one. Why not? So the third one says to take the vertices 9, 3, and 2 and take that as your cut. So you know what? Let me just draw it again here. Right? I mean, we know what this looks like at this point. Right? It looks like this. And so 9, 3, and 2 is the cluster is telling me to take. Now, how many edges does go from this set to the rest of the graph? Well, there's a bunch, right? There's 1, 2, 3, 4. Right? 4 edges cross this green line. 4 edges go between this group and the rest of the graph. So the Feedler density, the density of this cut of A3 B minus A3 is equal to 4 edges. How many possible edges are there? It's 3 times 7, 4 out of 21, times n, which is 10. Right, so this one has density 40 over 21, so it's about 2. Okay, and then what you do is, so you compute 10 different densities, and you just take the sparsest cut amongst those 10 possibilities. Okay, and notice that when you get to this point here, these 5 vertices will be this group of 5, which is sort of the cut that we were expecting to see. Okay, so in this graph, because it's such a nice graph, the vertices have arranged themselves in a way that it actually did find the minimum cut, the sparsest cut, that's different than the minimum cut, which is exactly the one that you expect. Okay, so the benefit of this method is that it's very, very fast, right? You just need to compute the Feedler vector, and then you only need to compute n possible cuts. It gives you n potential cuts, and you just you output the sparsest of those 10 potential ones, rather than 2 to the 10 possible cuts. But again, it's just fairly sparse. It's not guaranteed to give you the sparsest one, but this is a pretty fast algorithm to find you a fairly sparse cut that just uses this Feedler vector, this eigenvector associated to the second smallest eigenvalue of the Laplacian. Okay, and then the last part of this homework problem is, I mean, it's not a homework problem, but now it's part of doing the lecture, is to consider the following function, which is n times the following thing. This is the sum over all ij in the edge set xi minus xj squared divided by the sum over all possible I and j, and let's choose an order, so I is less than j, of xi minus xj squared. Okay, so what is this thing? Notice that this top part is exactly the quadratic form associated to the graph Laplacian that we discussed last time. We said that the Laplacian gives you this quadratic form. It exactly adds up all the xi minus xj squareds, where ij is an edge in your graph. Okay, this bottom one adds up all possible xi minus xj squareds, where I is less than j. So you only have x1 minus x2 squared. You don't have x2 minus x1 squared. Right? Now, what you're supposed to show in this problem is let A be any set. We're going to define the characteristic vector of A to be the vector whose entries are 1 if the node is in A and 0 otherwise. Okay, so for example, the set that we've been taking the whole time, except on the last slide, this set here, its characteristic vector just records which elements, which nodes are actually in your set. That's the characteristic vector of this set. And it turns out, and it's actually not so hard to see this, but phi of A slash B minus A is just going to be Q of the characteristic vector of A. Okay, why is this? This is because think about what happens when you plug this characteristic vector into this quadratic form. Okay, in the numerator, every time you have an edge in G, so for example, there was an edge from 1 to 6 in our graph, right? So that will be one of the terms in the sum. You will add up x1 minus 2, 3, 4, 5, x6, and you'll square it. So you'll add up a 1 for every single edge that goes from the vertices that are in your set. I've missed a 1, of course, to the ones that are out of your set, because then you'll get 1, 1, and 1, 0, and the difference will be 1, and you'll square it, right? So you'll get 1. If there's an edge that's totally within your set, it'll be like a 1 minus 1, so it won't contribute anything. If you have an edge totally outside of your set, it'll be a 0 minus 0, so it also won't contribute anything. So if you plug the characteristic vector into the numerator, it counts the number of edges between A and the rest of the graph. Okay, in the denominator, it'll count up all possible edges. Because what you'll do is you'll add up all possible, like this entry minus this entry squared, and this entry minus this entry squared, etc. Well, if you add them all up, what are you going to get? You're going to get 1 every time you had a vertex that's not in A and a vertex that is in A. In other words, you're adding up all the possible edges from vertices in A to vertices not in A. So this quadratic form is a very nice quadratic form. What it does is, if you feed it a characteristic vector, it spits out the density of that cut. Okay, so in principle, you plug in all possible characteristic vectors, and then you plug them into this quadratic form, and the smallest number that you get will be the sparsest cut. But as I mentioned, there are 2 to the 10 possible characteristic vectors in this case. There are 2 to the n, and 2 to the n is a humongous number. Right? You would have to test 1,024 possible things. That's every possible subset. The great benefit of this algorithm that you will code up is that you only need to test 10 things, right? You only need to test the 10 sets that you get by looking at this reordered Feedler vector. So you only need to consider the set containing just this node, then the set containing these two nodes, then the set containing these three nodes. So you only need to look at 10 possible sets. You find the sparsest cut among those, and that gives you a nice approximation of the cut that you would need to separate your graph into two pieces. Okay, so again, you really need to code up an example yourself in Julia. There's an example to do from the star problem in the notes, so please do that. You part of the point of this course is for you to get familiar actually implementing ideas of linear algebra and actually doing them, right? For that reason, I'm not even going to provide you my very brief Julia file, although I did show it on screen, right? So you could recreate it, but there's some value to actually typing it in yourself. Okay, also, since I consider this to be kind of a longer lecture because you have some assignment to do with this lecture, I will try to make the next lecture a little bit shorter, even though the total amount of time you have to watch this is going to be under 50 minutes. Let me also encourage you to click on the link in the notes that takes you to a nice post on spectral clustering, including the example that we worked through today. There's some other cool stuff in there. So let me pull up this picture, which is a picture of the Eigen values of the Laplacian. Okay, so remember that we talked about how, okay, so this first value is actually equal to 0. And the second one, this Feedler value, would be 0 if the graph was disconnected. Okay, so notice that it's a very small value. And the fact that it's small is reflecting the fact that the graph is kind of pretty close to disconnected, right? Again, the graph looks like this. Right, the graph looks like this, and it's pretty close to being disconnected into two pieces. And so that's reflected in the fact that the second smallest eigenvalue is rather small. Okay, then we have a little bit of a gap, like right, so this is like about 0.3. Then this is about 1. It might actually be 1. I didn't actually compute it. And that's also like, it's a pretty small gap. Notice that there's a much bigger gap between here and here. Right there, you go from like 1 to 3, so there's a gap of 2. But amongst the first 4, there's a gap of 0.3, then gap of 0.7, and then no gap. So this sort of place where there's a big gap in the eigenvalues also tells you some data about the graph, right? So it tells you that you could, this small first or second eigenvalue tells you that you're close to being sort of a graph that you can break into two pieces. And actually what this is saying, because they're pretty small up until this line, is saying that actually it's pretty close to a graph that you can cut into 4 pieces. And hopefully you can see that, okay, so these vertices, I could maybe group these end vertices, the ones that were 1 and 6, are sort of equally connected to the top and the bottom. But really, it looks like there's kind of like 4 clusters, and then these 2 vertices are kind of like they're part of 2 clusters, right? But that's actually reflected in this set of eigenvalues. The set of eigenvalues knows how connected your graph is. And so the size of these eigenvalues, when they're close to 0, sort of tells you that, oh, there's like roughly more components to the graph. Okay, so hopefully this is a very convincing argument, at least a convincing illustration, that the Laplacian matrix contains a lot of information about the graph. But again, that's kind of tautological because the Laplacian matrix contains all of the information about the graph. But if I just look at the 10 eigenvalues of the graph, it contains some really key information about the graph, and you don't need to remember the whole graph. You just need to remember the eigenvalues. So this is like the set of eigenvalues is often called the spectrum of a matrix. And so there's this whole field of math called spectral graph theory. And I mean, I'm grossly oversimplifying here, but that's like, can you understand a graph by looking at its spectrum? And the answer is you can understand quite a lot about it. Okay, and then there's also some really nice figures in that article, which again I encourage you to click on in the notes, with a cool application. And let me pull it up, which is imagine you had this data set and you were trying to, right, maybe you're trying to separate the data, right? Each point represents something, and you're trying to separate into two populations. Okay, looking at it with your eye, hopefully it seems pretty clear that this group of dots belongs to one population, and then the thing that I've outlined in green, those dots sort of belong to another population. Okay, but if you had this kind of data, how could you tell numerically where to place these, how to split this into two populations? Notice that it's not just how close the points are to the other points, right? Because like this point and this point are very far away, right? This point and this point are much closer to each other than the 2 points on the edges. So it's not just about which points are close to one another, right? So there are, I mean, this is an important question, I guess, in data science. Like how exactly do you separate out groups like this? One way to do this, though, is to use this idea of spectral clustering, okay, which is one way to approach this problem is you can take this data and form a graph out of it where you have a node for every dot and you just connect it to the 5 closest points to it, right? So you imagine that I draw in lots of edges here where for each dot I connected it to its 5 closest neighbors. Then you run the spectral clustering algorithm that we just saw. And basically there's going to be pretty few edges going between the red circle and the green circle, right? Like maybe this dot is connected to these 2 dots because maybe it's closer than its 5 closest neighbors, right? Maybe this dot connects to here or something, but there'll be relatively few edges crossing the boundary. And you should be able to detect that using the spectral clustering technique that we talked about today. Okay, so not only is this hopefully an indication that you can tell a lot about a graph from the eigenvalues of these matrices, hopefully this is also an argument that positive semi-definite matrices are actually extremely important, because this graph Laplacian, this mysterious kind of mysterious positive semi-definite matrix, you can get a lot of juice out of it, right? You can squeeze a lot of juice out of this orange. Okay, so next time we're going to move on to another application, distance realization, and that section is a bit shorter in the notes, and so I'll make that a shorter lecture. Probably we could all use a little bit of a break right around now, and this lecture, since I want you to go through and code it up yourself, I will assume will take you a bit longer than watching a normal lecture. All right, see you next time for distance realization.